In this lecture, we're going to look at continuous dynamic optimization using phase diagrams to look at the stability of the particular system of equations that we look at. So there are some computational issues. The continuous time problem has solutions that are of two types. We can find a steady state solution, which we discuss under our optimal control unit, or we can find optimal paths using phase plane diagrams, and we can find these optimal paths using software such as Maple, Mathematica, or even R to solve numerically a system of differential equations. Essentially, we require some form of discretization, which implies we might as well use discrete dynamic optimization or a mathematical programming approach, such as nonlinear programming, and then make use of a software package such as LP-Solve in R or the GAM suite of packages, which we'll discuss again under our optimal control unit. Here we demonstrate how to create phase plane diagrams, or sometimes they're simply referred to as phase diagrams. And we do this because it's more difficult to look at stability of systems, so the second order conditions, if you like. It's easier to do that using phase plane diagrams than it is to try and calculate the eigenvectors and eigenvalues from some of the square matrices that we develop out of the parameters of the system. So let's look at phase plane diagrams. We use them to investigate stability of solutions to systems of differential and difference equations based on the parameters of the equations, rather than having to solve the equations completely. Sometimes solutions to differential and difference equations can be difficult to obtain, and the phase plane diagram often provides enough information, particularly for the economist. For single difference or differential equations, the roots of the auxiliary equation must all be less than unity in absolute value. Otherwise, we end up with results that don't have any stability at all. We saw that a geometric representation of the solution in Ty space confirmed the algebraic rules for stability. Time paths that were damped over time were associated with roots less than the absolute value of 1 in the difference case and less than 0 in the differential equation case. For systems of equations, the characteristic roots of the coefficient matrix of the system must similarly all be less than unity in absolute value. This is difficult with n-equation systems when n is large, but in many economic applications, the number of variables whose equations of motion are involved is often very small and frequently only 2. In fact, we're going to look at the next set of lectures, and we'll see that the most problems can be looked at by having only 2 variables and 2 equations of motion. First order conditions evolving from the maximum principle approach, and again, see the lectures to come, consist of a pair of differential equations. So let's look at linear differential equations using phase diagrams. So we look at a homogeneous first order linear differential equation, a0 y dot plus a1 y equals 0, and it has the solution that y is a function of t, where the function of t is equal to this initial value c0 times e to the power bt, where b is minus a1 over a0, a1 and we take the negative of that. One can represent the original equation in y dot space, sometimes called or referred to as phase space, and this is done in the diagram that we'll come to shortly. For all points above the horizontal axes, y dot is greater than 0. As t increases, the direction of motion for y is rightward, so y is increasing. For all points below the horizontal axes, y dot is less than 0, thus y decreases and the direction of motion is leftward as t increases. This observation allows us to introduce the influence of t, time, in two-dimensional space by using arrowheads on the function y dot dy dt equals by to indicate the direction in which y would move as t increases. For the homogeneous first-order linear case, a necessary and sufficient condition for stability is a negative slope to the line in phase space. i.e. that b is less than 0, as we found previously when we looked at those solving a single differential equation. For the non-homogeneous case, and we'll only look at one, for the non-homogeneous case, the effect of a constant term is simply to shift the equilibrium value of y rightward or leftward away from the origin along the horizontal axis. So let's look at the influence of t on y dot equals 1/2 y and on y dot equals minus 3y. So we see here that we have y dot minus 3y gives you this line here, this isocline we will call it, and y dot equals 1/2 y gives you this isocline. So any position on this line means that y is increasing, and if you're on this part, y is decreasing as indicated by the arrows. So y is decreasing over time if you're going along this line, and if you're positive, it's increasing over time. With the function y dot equals minus 3y, we have that y is decreasing if we're to the above the horizontal axis, and here y dot is decreasing if we're below the horizontal axis. That means that you're going to come here. So with this function, you tend to move towards 0. With this function, you tend to move away from point 0. So if you happen to be just off of 0 here, you're going to move away from it in this direction. But if you're off in this direction here along this line, then you move back toward it. So in that sense, this is an unstable solution for y dot equals 1/2 y and a stable one for minus 3y. Consider another one. Here we have a non-homogeneous case where we have y dot is 1/2 y plus 2 and y dot is minus 3y plus 9. So here we have our equilibrium. Again, we move down away for this function. As time increases, we move in this direction, but if we're above the horizontal axis, we move in this direction. So we'll move towards this center point if we're to the left of it, and away from it if we're to the right of it, as long as we're above that y horizontal line. For this one, same thing, we move down here, away from this point till we get to here, and then in this direction, we again move toward that point there. So that's how we deal with a non-homogeneous case. A pair of linear homogeneous differential equations, y dot 1, a11y1 plus a12y2, and y dot 2 is equal to a21y1 plus a22y2, has a solution which is given by this form here. For example, y1 is then equal to k11e to the lambda 1t plus k12 e to the lambda 2t. Now we get the y1 and the y2, the lambda 1 and the lambda 2 from our characteristic or auxiliary equations, and the kij values will come from initial conditions. So given this solution, one can construct a picture in y1, y2 space. So previously we had looked at y and y dot space. Now we're looking, because we have two variables, y1 and y2 space. If you look back here, we have y and y dot space. So we really can't talk about this being an equilibrium in any sense. Now, knowing kij and the lambda j, one can vary t. For each value of t, we find associated y1 and y2, thereby tracing out a trajectory in y1, y2 space using arrowheads to indicate the direction of motion as t increases, and as we did in the previous two diagrams. For a set of differential equations at the top of this slide, so these differential equations here, y1, y2 space is known as phase space of a phase plane. Trajectories in phase space are often called phase paths or phase curves. So let me just underline that. So we have phase paths and phase curves, as we call them, and we have phase space of the phase plane. And the phase plane plus the path are referred to as the phase diagram. So we have this phase diagram here, and that's what we're going to be drawing in Y1, Y2 space. This offers potential for confusion, however, as phase diagrams for single equations were drawn in Y dot space. So now we're going to convert it to Y1, Y2 space, and we're going to leave out the Y dots. So consider the following example where we have Y1 is equal to 5e to the minus t plus 6e to the minus t, 2t, and Y2 is t 2 times e to the minus t plus 10 times e to the minus 2t. So this is the solution to a system of two differential equations. So values for y1 and y2 can be calculated. So for y1, at time 0 we get 11, at time period 1, 265, 2, 0.78, 0.26, and for y2 we get 12, 2.09, 0.45, and 0.12. And if we look at the trajectories for y1 and y2, they tend to be very similar. These numbers are very close, and in this diagram here, we don't distinguish between them. So that means that when we think of those diagrams, what we have is this result here and this result here. These should be corrected slightly because they shouldn't have a dot. Phase plane diagrams represent a form of solution to a system of differential equations. Alternatively, we could have found lambda in the solution from the auxiliary equation and used algebraic rules to determine whether or not the system is stable. More useful would be a means of establishing at least the general shape of the phase curve and the orientation of the arrowheads without having to find the eigenvalues of that matrix A that we had looked at previously. How can the system itself, a pair of linear homogeneous differential equations, help us to develop the geometry in phase space? Well, consider the following example where y dot 1, so the motion of the first variable, is equal to 5y1 plus 3y2. So in other words, the second variable influences the first variable, and the second variable, the equation of motion, is y dot 2 equals 2y1 plus 10y2. The slope of a curve in phase space is given by y dot 2 over y dot 1. In other words, we get dy2 with respect to dt divided by dy1 with respect to dt, and the dt's cancel, and we get 2y1 10y2, the y dot 2, the y2 dot rather, divided by 5y1 plus 3y2, which is the y1 dot. Lines through the origin in y1, y2 space have the general representation that y2 is equal to k times y1. Setting y dot 2 equal to 0, if we set that equal to 0 here, so we make that equal 0, then solving for y2 gives us y2 is 1/5 y1. So k is equal to 1/5. Along the line y2 equals 1/5 y1, the slope of the phase path is given by this here. This is your slope of the phase path, which we see is equal to dy2 divided by dy1. So the partial, or the derivative of y2 with respect to y1. So we get 2y1 plus 10y2 divided by 5y1 plus 3y2. We're going to substitute in this y2, we're going to substitute this value 1/5 y1. All right, and we'll first denote it by k. So we get 2y1 plus 10ky1 divided by 5y1 plus 3ky1. The y1s disappear, they cancel out. So we get 2 plus 10k divided by 5 plus 3k. We put in for k the 1/5, which comes from here, and we end up with 5/7 as being the slope of the phase path. The shape of the phase diagram begins to emerge independent of knowledge of the solution values. Curves along which the slopes of the phase path are constant are called isoclines. Along the horizontal axes, y2 equals 0. So then y dot 2 over y dot 1 is equal to 2/5. Along the vertical axes, y1 equals 0, and y2 over y dot 2 over y dot 1 equals 10/3, and so on. So now, if we look at the phase plane diagrams here, so we get, when y dot 1 equals 0, we get 5y1 plus 3y2 equals 0, so that y2 is negative 5/3 y1. Likewise, we've seen that for y2 dot equals 0, so the derivative of y2 with respect to t, we get that k equals minus 1/5. The red line is an isocline, so we've calculated this red line for y1 dot 0, and its formula is given by y2 equals minus 5/3 y1. So we're only going to look at this one for now, and we ask which way will y1 move in the areas to the left and right of the line, y1 dot 0. So remember, y1 dot is equal to 5y1 plus 3y2. So let's pick some points. So let's pick point 1, 1, which lies around here. And at point y1, or 1, 1, 1, or pardon me, 1, 1, y1 dot is equal to 5 plus 3 equals 8, which is greater than 0. So in other words, y1 increases as we indicate with this blue arrow. Now we pick minus 1 and minus 1, so we pick a point down here. And what do we see? Well, when we plug that in, y1 dot is equal to 5 times minus 1 plus 3 minus 1 is minus 8, which is less than 0. So as time increases, y decreases. Pardon me, y1 decreases. So we can look at other points. So we represent the decrease here by this arrow. If we look at point 3 minus 3, then we find that y1 dot is 6, and it's greater than 0. So at 3 minus 3, so 3 on the positive axis minus 3, and we get that the arrow of motion over time is to the right. And if we pick the point minus 2, so here's minus 2 plus 2, and we get it moving to the left because when we plug that in, y1 dot is equal to minus 4. So these arrows determine the direction of motion of y1 in this case, because we're looking at the y1 dot isocline. It's moving away from, or y1 is increasing to the right of that red line, the isocline, and to the left, it's moving to the left. Now we can do the same thing with y2 dot equals 0, and we look to see whether y2 is increasing or decreasing above and below the line y2 dot equals 0. And the arrows here provide those answers. All right, as long as we're above that y2 dot equals 0 isocline, which is defined by y2 equals minus 1/5 y1, we move. y2 increases when we're above it, and it decreases when we're below it. So we can attach these arrows, and any point between these two lines going to increase y2 and decrease y1. On this side, it'll increase y2 and increase y1. Over here, decrease y2, increase y1, decrease y2, decrease y1. You'll notice that if you pick any point here, the motion is going to go in this direction. If you pick a point here, it's going to go in that direction. Pick a point here, it's going to go in that direction. Point here is going to go in that direction. So it's very clear that the equilibrium point at 0 is unstable. Finally, we can define what is called a separatrix, which is a line in phase space with the property that the slope of the phase curve is the same as that of the line. A boundary, in other words, in phase space that phase curves can never cross. if in y1, y2 space, if a point were on a separatrix, it would continue its motion through time along that line, inward or outward, depending on the arrowhead orientation. So consider again the following example. Y1 dot equals 5y1 plus 3y2, and derivative of y2 with respect to time equals 2y1 plus 10y2. The slope of the phase curve is given by y2 dot over y1 dot, as we noted before, which was equal to the derivative of y2 with respect to time divided by the derivative of y1 with respect to time. The dt's cancel, so we get dy2 over dy1, which is a slope, which is 2 plus 10k plus 5 divided by 5 plus 3k. Now the slope of the separatrix and that of a phase curve along it, so dy2 dy1, which is the slope of the phase curve, must be equal. So we get 2 plus 10k over 5 plus 3k, which is the slope of the phase curve, and we say that the slope of the separatrix is k, so that implies that 3k squared minus 5k minus 2 equals 0. Thus k1 is minus 1/3, and k2 is 2. So we get two separatrices. y2 equals minus 1/3 y1, y2 equals 2 times y1. So as a further illustration, let's consider a slight variant of the ones we just looked at, all right, by looking at y1 dot equals 5y1 plus 3y2, and y2 dot equals minus 2y1 plus 10y2, which gives us these two phase curves, these isoclines. All right, we find the separatrix as y2 dot divided by y1 dot, set it equal to k, and each k will be a bit different. All right, so we get 2y1 plus 10ky1 minus 5y1 plus 3k1 equals k. And we find that k is equal to 15 plus or minus 14.8.18 over 6. So k1 is 4.86 and k2 is 0.14. So we get the separatrix. So y2 equals 4.86 y1, y2 equals 0.14 y1. These are the two separatrices. And we can draw this diagram now as follows. We have y1 here, y2 here. This represents our isocline y1 dot equals 0. This one represents, the blue line represents y2 dot equals 0. The red lines represent the two separatrices, and we then can figure out using the method above, where we look to the right or left of the y2 dot line and the y1 dot line, we can get the direction of motion, and we find that the direction of motion is given by these green lines with their arrowheads. So you'll notice one thing, that we're turning away from the point here, which is the solution. And what we find is that if you're on this separatrix here, you notice that the arrowheads both point towards the equilibrium point here, whereas for this separatrix, it's going to be away from the center here where our equilibrium point is. So what that implies is that if you start off on a point here, or indeed any point along this red line, you're going to reach the equilibrium. However, if you're off of that line at all, you're going to go away from equilibrium depending on the exact direction and where you start off. So we refer to this as a saddle point equilibrium because your saddle is given by this red line and everything falls off of it to one side or the other. So let's look at a couple of other situations here, and you can figure these out in more detail. Here we have where y1 dot is equal to minus y1 plus 2y2, and y2 dot is equal to minus 2y minus y2, and we end up with a spiral. Now notice here I've got these red lines, all right, and they indicate that for y1 dot we have a vertical line. So this blue line, even though it's poorly drawn, should be vertical when it crosses this particular y1 dot equals 0 line. And if it crosses this one, it should be horizontal, as given by that little red marker. This one again, these two, we have a vertical, and here we have a horizontal. All right, which implies that if you're at y2 dot line equals 0, then there's no change occurring. And likewise, there's no change here when we're on this y1 dot equals 0 line, because you're not moving away from it, you're right on it. So if we look at this other one here, where y1 dot equals y1 minus 2y2, and y2 dot equals 2y1 plus y2, we've just changed the signs in this one. Again, we're going to get a spiral that's similar to the one above it. Okay, the final one that we're going to look at is one where we have an isocline that's a 45-degree line. So y1 equals y2, or y2 equals y1. And we get that the derivative of y1 with respect to t equals 2y2. And the derivative of y2 with respect to t is minus 2y1. Notice that here only y1 enters, here only y2 enters. Y2 dot divided by y1 dot is equal to minus 1. That determines the isocline, which in this case is that 45-degree line. In reality, if one were to solve this, one would get a complex conjugate root, but with alpha equal to 0. So this system gives a number of circles. This isn't quite a circle, but it's supposed to be. And this is the direction of motion along the circle. So anywhere you end up, if you end up here, you end up going in a circle like that, and so on. Now, if y2 dot were equal to minus 4y1 instead of minus 2y1, then we would get elliptical shapes. We'd get more of an elliptical kind of motion. Okay, we will give some more examples of this in the next lecture. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.